Hello students, in this video we'll begin a discussion of fully nonlinear first-order partial differential equations by using Monge Cones. So let's consider the first-order PDE. We're going to do this in classic notation, f of x, y, and then we'll say u using the solution, and then p and q equals 0. This is a standard notation for first-order partial differential equation, just to x and y, right? So here, u is u of xy, p is partial u partial x, and q is partial u partial y. Okay, excellent. And so now we're going to assume that it's first order, so we need a non-degenerate condition. We also assume that fp squared plus fq squared is not equal to 0, so it's actually a non-degenerate PDE, okay? And so now we fix a particular point on the solution curve. So suppose that there's a point x0, y0, u0 is a point on the solution. Curve, solution surface. Okay. And then in particular, what this does, this gives me a relationship between p and q now. Then this implies that we have a relationship between p and q, namely what? Namely, f x0, y0, u0, p, q is equal to 0. And so by the implicit function theorem, we know that this defines q as a function of p. We can write f of x0, y0, then u0, p, and then some function q depending on p equals 0. Now, in particular, what this does is this allows me to say that there's a one-parameter family of tangent planes. Hence, there's a one-parameter family. So hence, there's a one-parameter family. Of tangent planes. Okay, what they look like? They look like u minus u0 is equal to p x minus x0 plus q of p y minus y0. Okay, and so in other words, what has to happen on the solution for the solution to this PDE to exist, it has to be a point of contact with all of these tangent planes over here. So what's going to happen over here is we have a whole bunch of different collection of planes, right? So here's a plane. This would be the normal vector of that thing over there. That'd be p, q, -1, right? You might get another plane in that one parameter family, like that. And that might be like a P1, Q1. You might have a P2, Q2, -1 for that normal vector. And the point of interest now is that these planes, as I look at their envelope, all the things that they collide, what we see is we're going to get a cone. That's tangent to both those planes. And so the envelope, I'll remind everyone what envelope is in a second here. The envelope of these tangent planes is the Monge cone. Okay, excellent. And so in particular, any integral surface of this differential equation has to have a tangent plane that's tangent to the Monge cone, right? So in particular, any solution to the PDE must have a tangent plane P tangent to the Monge cone. Okay. And so now we're in the business of finding a solution by tracking all these cones as they evolve over time, right? And then let me just remind you what these envelopes are. So recall, if you have a family of surfaces of w of x, y, and a, equals z is a family of surfaces, then you can differentiate this equation with respect to a. So partial a, w, x, y, a is equal to 0. And you can solve these equations over here to find a as a function of x and y, right? If we eliminate a, so eliminate a. If we do so, we're going to have a surface, z is equal to w of x, y, and then some other function that is a result of solving that system, f of x, y. Okay? And this is the envelope surface. So this is the envelope. This is the envelope. It's easy to see what these envelopes are. So for example, a real simple example of an envelope, even of course a cone is one of the simplest ones. If I look at this family of spheres over here, x, right? Then what would the envelope of this family of spheres? These are spheres that are moving down the x-axis, right? Whose center is at a, 0, 0, right? What would the envelope look like? Well, if you imagine those spheres moving down the x-axis, I can envelop that with a cylinder, right? So if I did the a derivative of this thing, I would just have 2x minus a is equal to 0, and so x minus a is equal to 0. Therefore, the envelope of this surface over here is just y squared plus z squared is equal to 1, and that is the envelope for that family of spheres. We can do the same thing with our family of planes. Now what we're going to do in the future videos, we're going to take this Monge cone over here, we're going to use a Monge cone to define what the solutions are. So this gives us the geometric picture of how we're going to use these cones when we're solving the PDE. Now we're going to transition to the Lagrange-Chapuis method, which is going to find the characteristic lines, and these characteristic lines have to be such that when we look at they have to follow a strip of tangent planes, and those tangent planes all have to be tangent to the Monge cones at the point generated by the PDE. Thank you very much.